Okay, Assalamualaikum and hi to all my students. Okay, so this is part 3 for this video of subchapter 2.2 phase diagram. In the previous video, we have learned a little bit about the binary eutectic phase diagram, and that video focus on no solid solutions. So in our syllabus, uh, we also have to learn about the eutectic phase diagram, the same as in the last video, the same eutectic phase diagram, but in limited solid solutions. So before this, we have a binary eutectic phase diagram for a complete solid solution, and for this video, we study the eutectic phase diagram in the limited solid solutions. So without wasting any time, let's get started. So what is the limited solid solution? Okay, you have to know first the limited solid solutions where the components are completely soluble in this liquid state, okay, but limited solubility in the solid state. Okay, it completely soluble in liquid but not completely soluble in solid. So that is the meaning of the limited solid solutions. Okay, as shown in this diagram, you can see that the difference between the limited solid solution and the complete solid solutions, you have this region. Okay, before this we do not have this region for the complete solid solution. Okay, so the limited solid solutions, there are 3 single phase region, of course, because we have the alpha here and the beta here and the liquid solutions here. So as we have learned, on the left side of the eutectic point, we call hypoeutectic, and for the right hand side, after the E here, E means for the eutectic point, we call it hypereutectic. Okay, so still the same, right? Okay, so the difference here, as you can see compared to the binary, okay, binary eutectic in no solid solutions, we do not have that region. Okay, but for the limited solid solutions here, we have this region. Okay, and then the information we can get from the phase diagram in the limited solid solutions, still this line refer to eutectic temperature, okay, or the melting, not the melting, the yeah, the TE, eutectic temperature lines. Okay, so this line is still we call the liquidus because it is the borderline between the liquid and the liquid plus solids. Okay, so this is hypoeutectic, and this right hand side is hypereutectic. Okay, but we have a new line here. This line we call it, if on the upper side we call it solidus and the lower side we call it solvus. Okay, so what is solvus and solidus? Okay, solvus denotes the solubility limit of beta in A, B in A. So this one is B, this one is A. So there is the limit for the solubility of B, and the solvers in DG here, solubility of A in B. The solvers in C and F here, the solubility limit of A. Okay, so this line refer to A because what can be mixed in A, and this line refer to A. Okay, how the limit, what is the limit of A when you mix the solubility in B. Okay, quite confusing, right? Okay, doesn't matter, we can see after this. Okay, so the other things are quite similar to the no solid solutions. Okay, and for this line right now we call it TM. What is the TM? Here is the melting temperature. Okay, for what element? For the element here. So in this phase diagram, we have the copper. So this one is the melting temperature for the copper. And for the right hand side here, this one is the TM for the B. Let's call this B and this A. So here is the B, melting point temperature for B. So in this case we have argentum, so this point around 1780 approximately lah. Okay, is the melting point temperature for argentum. Okay, so that point give us the information of the melting point temperature. So the eutectic point still the same, the triple point here. And then eutectic temperature also the same, the horizontal line that cross the eutectic point. Okay, similar to the binary eutectic in the no solid solutions, as we have learned in the previous video in the part 2. Okay, so to calculate the weight fraction, also still similar. Okay, quite similar. Let's jump to the example after this, and the eutectic reaction also quite similar. Okay, so the details you have to read by your own, because this subchapter is very what we call, it's very deep, so I don't want to cover all in my videos because it will becomes very boring. So let's jump to the example here. Okay, so this is the exercise in your notes, so there is no answers in your notes, but this is my versions note. Okay, so we have the example here, so make sure you write down the answers for your future reference. Okay, so this exercise shows the strontium and the by what's short form of element by, I forget, let me check first. Okay, bismuth. Okay, so atomic number of bismuth is 83. You can refer to your periodic table. I do not memorize every element in the periodic table, so when I forget something, I just refer back to the periodic table. Okay. Okay, so you are quite lucky during this pandemic, because for the quiz and the final exam later, you can open your book during the exam. Okay, so don't worry about that. uh, so label each phase region X and Y for the number 1 question. This is X and this is Y. So X closer to the sternum here on the left side. So we have beta plus liquid. Why we know it is liquid? Because this is the intermediate region between the liquid and the beta here. So the phase here is beta plus liquidus. Okay. So Y here, okay, Y is the lower region. See the same as in the no solid solutions eutectic. So this one is the complete solid, but complete solid of 2 elements here. One is the sternum and the one is the bismuth. So the symbol is represented by beta and plus and alpha here. So phase region in X is beta plus liquid L, and Y here is beta plus alpha. Okay, so the second question is determine the TM for pure sternum and bismuth. Okay, so this one, where the value of bismuth is 0, it's equal to 100% of sternum. So this is the pure sternum. Okay, this line. So this one, that point, particular point, is the temperature of melting point of sternum. Okay, so around 232. So if you do not get that accurate value, it's okay, but approximately around that value lah. So if you put the value of 200, it's totally wrong. But if you just approximate around 270, 225 here at the middle of that line, okay, at that 2 point, so around 230, 235 or 240 is still okay. Okay, so the melting point temperature for the bismuth, okay, on that point, because this is where the pure of bismuth is 100% composition. So the melting point temperature here for bismuth. Okay, so around here is 275, and then you use your ruler to get that straight line to find this value. Okay, so if I put it 275, also still okay, because we just refer on this diagram, not the software, so we do not get that accurate value. Okay, so the third question is to determine the eutectic temperature and eutectic composition. Determine the eutectic temperature and the eutectic composition. So where is the point of eutectic? Still the triple point here, right? Okay, so the melting point temperature represented by this line that cross the TE. So TE here around if I make the approximation 1 to 5 here, so around 130 or 140 still okay here, at least in the region between 1 to 5 and 149. Okay, and then the composition here, you project to the x-axis and find that value. So around this one is 55. So if you put it 56, 57, 58 or 59, also okay, because it's just the approximation based on this diagram, phase diagram. And then there is the value of the composition, 50% weight fraction of bismuth. Okay, so still the same concept to find the information using the phase diagram. And example here. Okay, this one is covered in your notes, so you can study by your own for these slides. Okay, so let's go to the another exercise. Okay, for this exercise we have aluminum and what is the symbol of Si. Silicon, oh sorry, I forgot about that. This is one is the silicon. How can I forget the silicon symbol Si? Okay, this is the tin or aluminum. Aluminum, sometimes we call in English aluminum lah. Bahasa Melayunya aluminium lah kan. Okay. So aluminum here and the silicon here. So we still have limited solid solution because we have the region of the alpha here. So let's get to the question A. State the type of the binary phase diagram. Of course, as I mentioned, because we have this region for that alpha, so this is the binary limited solid solution, or you can write the full name binary eutectic phase diagram solid limited solid solutions. Okay, if we do not have this region, we have the straight line here. That one is eutectic phase binary eutectic phase diagram in no solid solutions. So that is the name for the diagram that we have learned in the previous video. Okay, so the question B, let's go to the question B. Identify the melting temperature of pure aluminum and pure silicon. Still the same question as before. Okay, so it's quite straightforward. Find this line and then you have melting point for aluminum, and find this line. This is the melting point temperature for the silicon. Okay, so this value is very accurate. Maybe it comes from the software, I think, but I do not expect you to get that accurate value. Just approximation from this axis value from the graph of the phase diagram. Okay, and then let's go to the question C. Identify the phases present at A and B. So A, we know that it is between the liquid and the solid. Okay, so solid here we have alpha and beta, where alpha may be represented by the aluminum or beta represented by the silicon. But here is more on the beta on the right side. So this is the liquid plus beta, and this one is the liquid plus alpha. Okay, so the question A, for the A is L and beta, and B here is the alpha and beta. So it is very easy and straightforward. And okay, we have another question D. Compute the weight fraction of each phase for an alloy containing 40% silicon at temperature slightly above 577 degrees Celsius. As shown in this diagram, 577 is the eutectic temperature, so slightly above at 40% here, slightly above, maybe around this point. Okay, so to find the weight fraction of each phase, as we have learned before, the same calculation and method. The WL, the weight fraction for the liquid, is where the value here represented by the CB, C beta, minus the value here is 40%. Okay, just write down the equation first. Okay, so here is 40%. This point here is 100%, 100% lah. So this one is the Cl, where it reached the liquid phase. So this value is given in the phase diagram, 12.6. Okay, so Cb 100 times 40, this one is Co, over Cb 100 minus that eutectic point, 12.6. So that is your value, 68.6%. So this is the weight fraction for the liquid phase. And then to find the beta phase, I just 100 minus 68.6, so you will get 31.4%. Okay, so as easy as that. And then this is the theory of the microstructure. Okay, I can skip a little bit because it's quite similar to the previous video that we have discussed about the microstructure. Okay, let's jump to the example. We don't have much time. Okay, so this is the summary of the binary eutectic phase diagram of the limited solid solutions. Okay, as you can see here, the hypereutectic on the left side and the hypereutectic on the right side, and hypereutectic you get this microstructure beta, and the hypo here you get the alpha here. Okay, for the pro-eutectic, still the same as in the no solid solution as in the previous video. Okay, so I think that's all for this video. We will continue in the next video about the invariant equilibrium, because this is quite different. Okay, another forms of alloy transformations. Okay, there are many other forms. Okay, so this one we will discuss in the next video. So thank you, take care of yourself, jaga diri untuk COVID, dan selamat belajar. Good luck. Assalamualaikum and salam sejahtera.